A photon is a particle of light. But what is that exactly? And is light really made up of particles? Stay tuned to this video and you'll find out. Before we delve into photons, let's first recap what we know about light. Light is an electromagnetic wave which is caused by a change in the electric and magnetic fields. Electromagnetic waves have the ability to accelerate charged particles, which is how they interact with matter. The larger the amplitude of the wave, the greater the acceleration. This view is mostly correct. However, things get interesting when you take a look at how electromagnetic waves interact with atoms. An atom consists of a nucleus made up of protons and neutrons. The protons are positively charged, while the neutrons are neutral. This gives the nucleus an overall positive charge. The nucleus is surrounded by electrons which are negatively charged. When the number of electrons is equal to the number of protons in the nucleus, the atom is neutral. The electrons have more freedom to move around than the protons in the nucleus. Thus, electromagnetic waves mostly interact with the electrons rather than the protons. It turns out, electrons can only exist at specific regions within the atom. These regions are called energy levels because an electron needs a specific amount of energy to exist in a given region. What's interesting is that in order for an electron to move to a higher energy level, it needs an exact quantity of energy. This energy can come from an electromagnetic wave, but only if the wave has the exact amount of energy that is required by the electron, which corresponds to the difference in energy between the two energy levels. When an electron is at the atom's highest energy level, it needs a minimum quantity of energy to leave the atom. When this happens, the atom gains a positive charge because it has more protons than electrons. A positively or negatively charged atom is called an ion, and this process is referred to as ionization. When an electron falls to a lower energy level, an electromagnetic wave is emitted that contains the same amount of energy as the difference between the two energy levels. What's even more interesting is that the amount of energy that an electromagnetic wave can deliver to an electron depends not on the wave's amplitude, but its frequency. The higher the frequency, the more energy the wave is able to deliver to the electron. If the frequency is too low, the electron will not jump to a higher energy level regardless of how much the amplitude of the wave is increased. This means if an electron needs a frequency corresponding to blue light, it will jump to a higher energy level when the atom is illuminated with blue light, regardless of how low the intensity of the light is. On the other hand, if red light is shined on the atom, it won't jump to a higher energy level regardless of how bright the red light is. This shows that electromagnetic waves are absorbed and emitted in discrete packets, with the energy per packet being dependent on the wave frequency. Increasing the amplitude of the wave only increases the number of packets that are emitted, but does not increase the amount of energy in each packet. An electron can only absorb a single packet of energy at a time. If that packet doesn't contain enough energy to move the electron to a higher energy level, or eject it from the atom altogether, the packet is not absorbed. This means the total energy carried by an electromagnetic wave is a multiple of a minimum quantity, which cannot be split up further into smaller parts. The technical term for a minimum quantity of energy is a quantum, and the quantum of electromagnetic energy is called a photon. The observation that a minimum frequency is required in order for an electron to be emitted from an atom is not that interesting in my opinion, because we can observe something similar in our everyday lives. For example, this ball will only leave the container if I move it back and forth with a high enough frequency. If the frequency is too low, the ball doesn't leave the container regardless of how much I move it. The more interesting aspect is that a single photon can only be absorbed by a single electron. This means even though an electromagnetic wave spreads out in space over time, a single photon worth of energy will still only be absorbed by a single electron at a single location. It's almost as if the entire wave disappears as soon as it interacts with a single electron. It's tempting to think that we can toss out the wave view of light entirely and instead think of light as being made up of tiny balls flying through space. However, light still retains its wave nature. even when the intensity of the light is reduced to a single photon. This means we still observe interference and diffraction patterns even when only a single photon of light is emitted. To make this easier to imagine, let's look at a simulation of photons passing through the double-slit setup that was used to prove the wave nature of light in the previous video. Let's start off with a low-intensity light source that emits a single photon at a time. The brightness of each block represents the likelihood of observing a photon at that point in space. Notice that only a single block lights up for each photon that is emitted. This means the light will only be detected at a single location at a given time. If we place a row of photodetectors some distance away from the slits, only one of the detectors detects a photon at a given time. The exact detector on which the photon lands appears to be random at first. However, as more and more photons land on the detectors over time, the double-slit diffraction pattern begins to emerge. This shows that even though the light appears to be made up of discrete particles, it is still diffracted like a wave. When we increase the intensity of the light source, the number of photons that are emitted increases. More blocks are lighting up at the same time, which shows that there are more locations in which a photon can be detected. If we keep increasing the intensity, the light starts behaving like a continuous wave. The double-slit diffraction pattern is now clearly visible. I'd like to emphasize that what you're seeing is a visualization of the discrete and random nature in which light is detected. This doesn't mean light is actually made up of discrete particles while it is traveling. In fact, we don't as of yet have an explanation for why light behaves like a wave while it's traveling but is detected as a particle. In our day-to-day lives, we mostly observe light as a wave because most light comes from high-intensity sources that emit a large number of photons. Moreover, individual photons of long-wavelength light have less energy. This makes it harder to detect them in isolation than photons of shorter wavelength light. In fact, the photon nature of light mostly becomes apparent in wavelengths shorter than visible light, which includes the ultraviolet, X-ray, and gamma-ray portions of the electromagnetic spectrum. At these wavelengths, individual photons have more than the minimum amount of energy required to ionize atoms. This makes X-rays and gamma rays particularly dangerous because their photons have enough energy to break apart DNA molecules. Now that we know what a photon is there any situation where we observe individual photons in our everyday lives? Well, actually, there is. Sort of. If you've taken a photo or video in low light conditions, you will have undoubtedly noticed that the image appears grainy or noisy. Part of this noise is caused by variations in the number of photons striking the image sensors. When more photons land on one sensor than the others, the image appears brighter at the pixel corresponding to that sensor. The effect of this noise becomes less apparent in brighter settings because the light contains more photons, resulting in less variation in the number of photons detected among the sensors. We can now answer the questions asked at the beginning of the video. Light itself is not made up of discrete particles, but its energy is absorbed and emitted in discrete quantities or quanta called photons. The amount of energy in each photon depends on the wavelength of the light. Light retains its wave nature even when its intensity is reduced to a single photon. Thank you for watching, and I hope you found this video interesting.